Today we're going to be talking about characteristics of exponential functions. And first we're going to start with domain and range. We've talked about domain and range before in this class. We talked about domain and range with linear functions and also quadratic functions. The domain of all of the functions we've talked about this year have been negative infinity to positive infinity. There's been no restriction on the numbers that we can substitute for x into the equations for any of the functions we've solved. We've done linear functions, y equals x, we've done quadratic functions, y equals x squared, and now we're doing exponential functions like y equals b to the x, and there's no limit on what we can put in for that exponent. So our domain for each of the functions we'll discuss today is negative infinity to positive infinity. Now the range of a function talks about the numbers that we can put in for y, and that's from the bottom to the top of the function. Now there are a couple of possibilities here, but remember that with an exponential function, the graph is limited by the asymptote, which either shows us that the bottom of the graph is the asymptote. So for example, if we had an exponential growth function, the bottom would be at the asymptote of the function, and the top of the graph would go up to positive infinity. And an exponential decay function will be similar. Even though it's decreasing instead of increasing, the bottom of the graph is still defined by that y equals k asymptote. So the bottom of the graph will be the k value, and the top of the range will be positive infinity. Both of these graphs are pointing up on the y-axis. Now, if our asymptote is above the graph, so let's say our asymptote is this horizontal line, that's not the best I've ever drawn, but the graph is a reflection so that it goes below the asymptote. Then the bottom of the graph, remember we start with the bottom of the graph points down to negative infinity, and the top is that y equals k asymptote. So our range will start at negative infinity and go up to the number for the asymptote. The same could be true if we were graphing an exponential reflection that would look like this. So let's look at a few examples and talk about what we see. This first example, the domain is going to be all real numbers, negative infinity to positive infinity. The range will begin at the bottom of the graph, and the bottom of this graph goes to the asymptote, and that asymptote is y equals 0. So the range starts at the bottom, which is at 0, and it goes up at the top to positive infinity. The next example, I'm going to go ahead and draw my asymptote here at y equals negative 2. The domain, again, is going to be negative infinity to positive infinity, and the range, the bottom of this graph, is at the asymptote with a value of negative 2, and the top of the graph points up to positive infinity. Our next example, here's my asymptote at y equals positive 1. The domain is going to be negative infinity to positive infinity, and the range, again, we start with the bottom. The bottom of this graph points down to negative infinity. And then as I follow the graph, the top tops out at y equals 1. My last example, the domain, again, negative infinity to positive infinity, and then the bottom of this graph is at y equals negative 2, so negative 2, and then the top of this graph goes up to positive infinity. The y-intercept and the asymptote are things that we've been discussing since day one of talking about exponential functions. The y-intercept is the point where the graph crosses the y-axis, and so we'll name it as an ordered pair with a 0 for the x-coordinate. Remember that if the function is in general form y equals a times b to the x, the y-intercept will be the a coordinate. But if there are other numbers added, like if you have a horizontal shift or a vertical shift, that's not true anymore. But that is a shortcut that we have for when our graph or our function is given in general form. The asymptote comes from the constant added to the end of the equation, y equals k. In general form, there's nothing added there, so it's y equals 0. The asymptote is a line that the graph approaches, but it never actually touches it or crosses it. It's like an invisible barrier or a boundary line. We're looking for the place where the graph goes flat. The other thing we're going to discuss in these examples is interval of increase and interval of decrease. The way that exponential functions work is that the entire graph is increasing if it's a growth function, and the entire graph is decreasing if it's a decay function. And so the graph does not change directions. Either the whole thing will be growth or the whole thing will be decay. And the same thing for reflections of those functions. What we'll do is we'll define the interval of increase as negative infinity to positive infinity, because the whole thing will be increasing. And then if it's decreasing, the whole thing increasing, then it will be negative infinity to positive infinity. And if the whole thing is decreasing, then for the interval of increase, we'll just write none. And then same thing with interval of decrease. If the whole thing is decreasing like this, we'll write negative infinity to positive infinity. If the whole thing is increasing, then there's none. So let's look at these examples. First, we'll identify the y-intercept, which for this equation or this function is 0, -1. The asymptote where this graph goes flat, is here at y equals -2. This graph moving from left to right, the y values are decreasing because it's going downhill. So the interval of decrease is negative infinity to positive infinity. The whole thing is going downhill, and the interval of increase is none. For our next example, the y-intercept is 0, 0. The asymptote goes flat here at y equals 1. The interval of increase is the entire graph. The entire graph is going uphill from negative infinity to positive infinity, left to right, and there is no interval of decrease. We talked about end behavior with linear functions and quadratic functions, and so it's a similar concept. We're trying to explain where the y values are going as we move to the left and to the right on the graph. As x approaches negative infinity is referring to the left-hand side of the graph, because in a coordinate plane, negative infinity is on the left of the x-axis and positive infinity is on the right. The positive numbers are this way, the negative numbers are this way. And the same with the y-axis. Up is positive infinity and down is negative infinity. So as we move to the left, we'll say whether the arrow of the graph is pointing up or down by telling if it's a positive infinity or a negative infinity, and then we'll do the same as x approaches positive infinity, referring to the right-hand side of the graph. Let's look at a couple of examples. So we want to basically start at the center of the graph, and then as x approaches negative infinity is asking, as I go to the left on the graph, where does the arrow of the graph go? So the graph is pointing down, and that is toward negative infinity on the y. And then the other way, as x goes toward positive infinity, moving this way on my graph, the arrow would be sort of going up, but it can't keep going up forever because the asymptote is in the way. So on this end, the graph is approaching the asymptote, which is y equals 1. So the y values are approaching 1. On this next example, moving toward negative infinity on the left of the graph, this end of the graph is approaching the asymptote, which is y equals negative 2. And then moving toward the right-hand side where x is positive infinity, the arrow of the graph points up toward positive infinity. On this function, negative infinity on the left, the graph is approaching the asymptote, which is y equals 0. And then on the right, if I start at the center of the graph and go toward the right, the graph is going up toward positive infinity. The last one, as x approaches negative infinity on the left, the y values are going up toward positive infinity. And as x approaches positive infinity on the right, the y values are going down, but just to the asymptote at y equals negative 2.